Hello, I'm Dawn Geatches, a computational scientist here at STFC, based in the Hartree Centre at Daresbury Laboratory in Cheshire. I explore the chemical and physical properties of materials using computational atomistic modelling techniques. And for this task, I've been looking at lattice energies. Lattice energy is the energy released when molecules come together and they condense to form a crystalline structure.
And I'm Rebecca Mackenzie, a data scientist at the Hartree Centre, working on statistical models of lattice energy. I've been looking at using the atomistic models as input to the statistical models, which will enable us to predict lattice energies from molecular structure. Lattice energies are important because they can be used to describe the solid-state properties of drug molecules, which are critical to the stability and bioavailability of pharmaceutical drug products. However, experimental lattice energy data for drug molecules is hard to come by. High-performance computing can potentially solve this problem by providing calculated lattice energies to plug the data gap.
Calculating lattice energies of organic molecular crystals can be computationally challenging, depending on the level of precision required, and can take a lot of time to set up the models and run the calculations. As a result, for many years it's simply been assumed that particular techniques and models are the best, and these have become the default go-to. Well, we've now been able to thoroughly and rigorously test a long-held industry-wide assumption, and our results suggest that an atomistic modelling technique based on force fields, in fact using force field compass 2, currently works the best for calculating lattice energies, and it even outperforms the more precise but more computationally expensive density functional theory.
So using a large data set with compass 2 calculated lattice energies for statistical model development and evaluation, we can predict lattice energies pretty well based upon molecular structure alone. Being able to get good estimates of calculated lattice energies, even without crystal structures, will be enormously beneficial for industrial scientists, as the related processability considerations can be integrated earlier into the development cycle, before the crystal structure is even known. With such a clear payback for involvement, this cross-industry combination of chemists, data scientists and leading industry experts has demonstrated this is a good blueprint for how to tackle the prediction of other important physicochemical properties.
Between us, we've identified the optimum atomistic and statistical models for calculating lattice energies. We've taken out the time-consuming work and produced a robust, multi-method modelling standard.
It's been of great benefit to be able to come together as a community with our colleagues at the CCDC, the Cambridge Crystallographic Data Centre, and the University of Leeds to build a model that describes a greater chemical diversity than previously published work, and to be able to blind test the predictive ability of our models with the industrial partners in the dock.
Any industrial scientists wishing to make use of the force field protocols, which were developed by Richard Mackenzie Robinson of the University of Leeds and myself, would be very welcome to contact either Richard or me. If you're more interested in the density functional theory methods, then please contact me.
And if you'd like to make use of the machine learning models for estimating lattice energy from molecular structure, I can supply you with the Jupyter notebooks which implement all of the required workflows.